Welcome to Pavingars, webinars for the pavement community. My name is Andrew Braham, and today we'll be talking about Rcurves characterization analysis for asphalt concrete. This is work that was done by Dr. Shu Yang toward his dissertation research, and the title of the paper is Rcurves characterization analysis for asphalt concrete. Dr. Yang received his bachelor's and master's of science from Southeast University in Nanjing, China, and his doctorate of philosophy from the University of Arkansas. If you're interested in learning more, you can click on his LinkedIn profile below in the comments section. Now, we've had a couple of previous Pavingars on a similar topic. There's a February 19th, 2020 Pavinar that talked about the master fracture curve. And then there's a December 27th, 2020 Pavinar talking about Rcurves in relation to binder grade, aggregate size, temperature, and loading rate. So we've already talked a little bit about some of the background behind Rcurves and the concepts behind Rcurves, so let's take a slightly different approach here. Let's dig a little deeper into the literature of Rcurves. Rcurve stands for resistance curve. And when cracking occurs, this is when the energy release rate equals the resistance of the material. And Rcurves quantify crack growth resistance. The first known example of Rcurves was from Irwin and Keiss in 1954, and what their research did is it plotted the resistance of a crack versus the crack extension. And since then, this has been applied in many areas, including metal and alloys, composites and epoxy adhesives, ceramic and porcelain, many different human applications, including tooth enamel and bones. So you can see on the right, this was a study done in 2012, and you can see the fracture resistance versus the crack extension, and it's looking at different bone types of people and how they resist fracture. And then also in the area of civil engineering and other material sciences, there's been work with Rcurves in rock, in concrete, and in polymers. Now, since we're talking about pavements in this series, we're going to take a quick look at these three, the rock, the concrete, and the polymer, because they have the most direct application to pavement usage. So starting with rock, this is a project from 2002, and it's a paper that was in engineering fracture mechanics, and it's titled The Rcurve Behavior in Notched Beam Tests of Rocks. And there was significant discussion on the three-point bend sandstone beam tests that were run. So the rock type was sandstone, and the testing geometry was a three-point bend beam. They used a linear elastic fracture mechanics for their analysis, and they used monotonic loading during the test. And what they found was that the asymptotic limit of the Rcurve compared satisfactorily with the fracture toughness. So you can see on the left, the fracture toughness was about 31.8 megapascals millimeters to the half. And then you can see that the asymptotic limit of the Rcurve ended around that region, about the 31 to 32, maybe 33 limit. Now, while they primarily looked at monotonic loading, they also looked at some cyclic tests. So you can see here in the area of rocks, there has been some work done. This is just one example. There's many more out there about using resistance curves in order to quantify and better understand the cracking behavior of rock. There's also been a lot of work done with concrete, and this is Shi and Bezant from 1997. So this is a little older. Also, though, from engineering fracture mechanics, and the title of the paper is Random Growth of Crack with Rcurve, a Markov process model. Now, these were three-point bend tests run on concrete, so the same geometry as the rock example, but instead of using sandstone, they used concrete. And what they did is they looked at the probability of the crack propagation and the probability of the failure of the concrete. And what they found was an increase in displacement led to an increase of the variable of the loads that were being applied. So this is kind of a slightly different take on using Rcurves. This was more of looking at what would happen trying to predict the cracking behavior of concrete. And they found that as the displacement increased, the predicting load also increased in variability. Now, one of the reasons I chose this paper specifically is Bazant is one of the leaders in the fracture of concrete. He has many textbooks, many journal publications, and he is more of a material science researcher, and so he treats concrete as a quasi-brittle material, which it is, of course, but kind of stepping away from the civil engineering perspective more into the material science perspective, looking at quasi-brittle materials, of which concrete is one example. And the reason that I mention that is another area of material science, polymer, can be related relatively closely to asphalt concrete. So this is from 1995, it's Bernal et al., and this was published in Polymer Testing, and the title is A Simple Method for Rcurve Determination in ABS Polymers. They looked at both pre-cracked and blunt notch specimens, so two different types of specimens, and then on this plot on the left, the data on top, or the open squares, is what they call the leveraged normalized method deformation function. And they use the Ramberg-Osgood type law. And what they did is they compared this prediction model to the traditional multiple specimen, which is the data on the bottom. So they used a method to predict cracking in polymer, and that was the top square functions, and they compared that to multiple replicates of actual testing. And so this is kind of similar to what Bazant did, is it's more of trying to develop models in order to predict cracking behavior. And the reason I specifically looked at this polymer is both polymer and asphalt concrete are viscoelastic materials. So when you look at asphalt concrete through the lens of material science, it's useful to look at it as a viscoelastic material, and that will open the door to comparison of many other materials. So this is just three examples of rock, concrete, and polymer. There are many more out there, but it gives you an idea of other areas that are looking into Rcurve analysis and some of the ways that they're trying to utilize it. Now, as I mentioned, when we were looking specifically at asphalt concrete and the Rcurves, the Pavement from December 27th, 2020 looked at binder grade, nominal maximum aggregate size, testing temperature, and loading rate. But today's Pavement is going to look at mixture type, test temperature, moisture conditioning, and aging. So you can see here on the right, this is a plot of three different levels of aging. There is the so-called 2-hour aging, which we label none, and that's because if you're mixing and compacting asphalt concrete in the lab, you will always do the 2-hour aging protocol. So that's kind of the baseline, which means there's no additional aging. But there are also protocols for short-term aging, which is a 4-hour aging, and long-term aging, which is a 120-hour aging. So you can see here the influence of aging on the Rcurves. In addition to aging though, let's take a look at these four variables in a little more detail. The mixture type, the testing temperature, the moisture conditioning, and the aging. So this research looked at three different mixture types. The first was traditional hot mix asphalt, or HMA, without wrap, and the mix design showed that this had 4.3% asphalt binder. The second mixture type we label HR, which is also hot mix asphalt, but it has 25% wrap. And with that 25% wrap, the total asphalt binder content was 4.6%, some of which came from the wrap source. WR is warm mix asphalt with 25% wrap, and this used 4.1% asphalt binder, and it also had a chemical in order to achieve those lower mixing and compacting temperatures, which was added 0.5% by weight of binder. So you can see HMA is hot mix asphalt without wrap, HR is hot mix asphalt with wrap, and WR is warm mix asphalt with wrap. All of the binders used a SBS modified PG76-22, and they all had a 9.5 millimeter nominal maximum aggregate size. Now the test temperatures were run at minus 12 degrees Celsius and minus 24 degrees Celsius, and this was based on a 2007 Transportation Research Record paper, and this is actually written toward my dissertation, and it was also including my advisor, Bill Butler, and co-advisor, Mihai Maristanu. And the title of that paper is Effective Binder Type, Aggregate, and Mixture Composition on the Fracture Energy of Hot Mix Asphalt in Cold Climates. And that can be found in Transportation Research Record number 2001, and that was published in 2007. But basically, the summary of these testing temperatures was the fact that we're using a PG76-22 asphalt binder. And if you look at that PG76-22, the BBR testing temperature, or bending beam rheometer testing temperature, is 10 degrees higher than the minus 22. So 10 degrees higher of minus 22 degrees Celsius is minus 12 degrees Celsius. So one of the testing temperatures matched the minus 12 degrees Celsius. Now we also added an additional test 12 degrees Celsius lower than that test temperature, which was minus 24 degrees Celsius. And the reason that we did this is traditionally asphalt binder grades go down in 6-degree increments. So we could have tested perhaps at minus 18 degrees Celsius, but we went down to minus 24 degrees Celsius because we wanted to span the glass transition temperature. And a very brief definition of the glass transition temperature is that the glass transition temperature separates the elastic and viscoelastic behavior. Below the glass transition temperature, asphalt concrete behaves as an elastic material because the asphalt binder is cold enough to become elastic. Above the glass transition temperature, however, asphalt concrete tends to behave in a viscoelastic behavior. So that asphalt binder is no longer elastic, it has a viscous component, and you get very different behavior. And Hussein Butler at the University of Wisconsin, Hussein Bahia at the University of Wisconsin-Madison has done a lot of work with the glass transition temperatures. Now, the nice thing is that when you get into this low temperature testing, you're avoiding any dissipated creep energy. So if we started going to higher temperatures than minus 12 degrees Celsius and minus 24 degrees Celsius, you start getting a lot of dissipated creep energy in your fracture test. And this is something that if you're in fracture testing, I encourage you to take a little bit of look at, is this relationship between testing temperature and asphalt concrete being elastic versus viscoelastic, and what kind of energy is being expended when you're running a test. And we ran the semicircular bender SCB test geometry, which is shown here in our lab, and we followed AASHTO TP 105, which is the low temperature SCB fracture testing protocol, and we used a Basler camera in order to take a picture of the face of the specimen during the testing. Now for moisture conditioning, we used an indirect tension type test. We used AASHTO T283 in both the unconditioned and the conditioned formed. So unconditioned is just testing the sample at ambient temperature. Conditioned is taking the sample and vacuum saturating it and putting it through a freezing and thawing cycle. So this gives you an idea of a conditioned versus an unconditioned test result. And you actually can then divide the unconditioned by the conditioned tension strength, and you can get the TSR strength ratio, the tensile strength ratio. And finally, for aging, we used AASHTO R30, and as I mentioned before, there are 3 levels. The unaged uses just the standard 2-hour loose prior to compaction aging protocol, and this is at compaction temperature. So again, if you're compacting asphalt concrete in the lab, you will always go through this aging protocol. Therefore, we're calling it unaged because it is the standard aging protocol. And I mentioned it's at compaction temperature. So for the HMA mix, that's 160 degrees Celsius. For the hot mix asphalt with wrap, the HR mix was 170 degrees Celsius. And the warm mix asphalt with wrap, the WR, was 140 degrees Celsius. So we ran testing after this unaged level. We also short-term aged samples, which is 4 hours at the compaction temperature prior to compaction. So it's double the length of the unaged. And then the long-term aging, you put the sample through the short-term aging protocol you compact it, and then you take that compacted sample and you age it for 5 days at 85 degrees Celsius. And this gives you long-term aging. So those are the moisture conditioning, the mixture types, the aging protocols, and also the testing temperatures. Now, how do we quantify the R curve? Well, in order to capture the data, as I mentioned, we used a bachelor camera. So this is an image of the bachelor camera, and we're recording this face of the SCB test. Our camera is 18 megapixels. It's an 8-bit monochrome grayscale, and the grayscale goes from 0 to 256, which is really nice for asphalt concrete because you can get that really nice aggregate skeleton in your images. Depending on the loading rate for these tests, we ran it at 0.03 millimeters per minute. And when we're running it at 0.03 millimeters per minute, we capture 0.2 frames per second, or 1 frame every 5 seconds. Now, on higher temperature tests, above these low temperature testing regions, we often use the loading rate of 1 millimeter per minute, for example, for like the iFit fracture test. And if we're running at 1 millimeter per minute, we capture 14 frames per second. So this gives you an idea of how many frames per second we use based on the loading rate of the test. We need to illuminate the sample face. Something you need to be very careful with is when you're testing at low temperatures, you don't want a light source that gives off heat. So you need to use an LED bulb. If you use a regular bulb, that actually does give off heat. And because you're just looking at the sample face, if it heats up a little bit, that may influence how that crack forms in that sample face. And we recognize that this is one of the challenges with using a camera is this sample that you see in this picture is 25 millimeters thick, and the crack forms throughout that entire 25 millimeters. But when we're taking a picture of the sample face, you're just looking at one dimension of a three-dimensional crack. So we recognize that that is something that needs to be taken into consideration, but that's the way that the data has been collected for this study. Now, when we get our images, basically what we're measuring is the cumulative fracture energy, and that's here on the y-axis, and then the crack length extension, which again is shown by that digital image on the sample face. We plot those against each other, and we get three components out of this. Now, here you can see there are three replicates. It has a relatively wide range of variability, and what we do is we take the average of those three replicates and we smooth it, and that is that solid line that's in the middle. We can quantify the crack initiation. This is also known as the cohesive energy, and this is a point, so this is when the crack length extension moves away from 0. Our crack propagation is the energy rate, and the energy rate is actually a slope. And then our fracture energy is a single point, and that's at the end of the test. And you can see fracture energy is quite commonly captured for fracture tests. We're adding, though, the crack initiation and the crack propagation, or the cohesive energy and the energy rate, to our data that's being collected. Now, if you want to calculate the energy rate, the slope, that's simply the fracture energy minus the cohesive energy, and that's divided by the total crack extension. For this research, what was found? Well, the effects of temperature, we found that the energy rate for the HMA and the WR, the lowest testing temperature, had the lowest energy rate. And for the fracture energy and the cohesive energy, the trends were not quite as clear. So what we found is that RAP may reduce resistance to crack propagation, but we feel that the warm mix technology could potentially counteract that resistance. So one of the things that we talk about when we use RAP is it is a little more brittle than virgin material and virgin asphalt binder, and we found that the warm mix could potentially counteract that behavior. When we looked at moisture conditioning, again, we focused on the energy rate. We felt that moisture conditioning reduced the ability to resist crack propagation. So again, this is not unexpected. When you moisture condition a sample, you reduce the bonding between the asphalt binder and the aggregate in some places. So it makes sense that we reduce the ability to resist crack propagation. What we were a little surprised at, though, is the fracture energy and cohesive energy. The trends were not quite as clear. We were expecting to see some differences there as well. So these traditional energy metrics, the fracture energy especially, may be missing some key performance behavior. So with our set of tests, the energy rate did pick up the moisture conditioning, but the fracture energy, which is commonly captured, actually did not pick up any significant trends. Now, when we look at just short-term aging, the fracture energy, the short-term aging equals or increases the fracture energy, and this is something that we've seen from other studies. While the mix may become a little more brittle, the softening curve portion is a little steeper, but the peak load is higher, so you actually get a higher fracture energy overall. Now, with the cohesive energy and the energy rate, the trends were not as clear, and we felt for the four variables we looked at, the testing temperature, moisture conditioning, aging, and mixture type, the effects of short-term aging was the least clear of those four variables investigated. This is sometimes frustrating in research to find that things are not clear. In my opinion, however, sometimes finding that things are not as clear is as important as finding clear trends. So this is the data that we had. We interpreted it as best as we could, but there may be some work that needs to be done in this area. Now, long-term aging, looking at long-term aging versus the no aging. All three parameters had a similar trend, the fracture energy, the cohesive energy, and the energy rate. We felt that the long-term aging reduced all three of these. And we felt that there was a difference between the short-term aging and the long-term aging, and this is good. This means that the long-term aging protocol that we've established, the AASHTO R30, is able to pick up differences with resistance curves. So in conclusion, our curves capture fracture energy, cohesive energy, and energy rate. The cohesive energy is related to crack initiation, and the energy rate is related to crack propagation. We felt that lower testing temperatures in general indicated a lower energy rate, and the moisture conditioning reduced the ability to resist crack propagation. We found short-term aging was similar to moisture conditioning, but it was kind of the least clear of all the trends we examined. And we felt that long-term aging reduced fracture energy, cohesive energy, and energy rate. So overall, we felt that our curves do show promise for quantifying cracking in asphalt concrete. We think it's something that should be continued to be looked at in different scenarios. If you're interested in learning more, the full paper can be found at the International Journal of Pavement Engineering. The DOI is also listed below, along with Shu's LinkedIn profile. And this is just a fun picture. I visited Shu. He is now at Hunan University in Changsha, China. I visited him and he was gracious enough to take me up to Zhangjiajie National Forest Park. And this is us going up there. It's a beautiful area. I really highly encourage you to visit if you have the opportunity. So as I mentioned, the links can be found below. And thank you for joining me today. I appreciate your participation.